Hi, I'm Katrina Hansen.
And I'm Tyler Johnson. And in this lab, we explored low-pass circuits, which amplify low-frequency sounds and block high-frequency sounds, and also high-pass circuits, which amplify high-frequency sounds and block low-frequency sounds.
We built the circuits using a 1 microfarad capacitor, a resistor, an LM348 op-amp, and a constant plus and minus 15 volt power supply. To choose the value of our resistor, we first decided on a frequency of 600 Hz, because that's where we wanted the cutoff for amplifying and blocking the frequency. We used the equation frequency equals 1 over 2 pi RC to calculate a resistance of 265 ohms. We used a 270 ohm resistor giving a 589 Hz frequency. First we did a high-pass circuit by connecting the resistor to the output of the op-amp.
Here is our high-pass circuit built in LT Spice. We ran the simulation with the input frequency of 589. The input is shown in green and the output in blue. The output is 90 degrees offset and has a gain of 1, and this is expected because the circuit has a cutoff point of 589 Hz.
We then changed the frequency to 100 Hz, and we found that the phase difference remained the same, but the gain was 0.2. We then changed the frequency to 1000 Hz and found that the phase gain remained the same, but we had a gain of 1.7.
We built a LabVIEW VI to graph the input and output frequencies of the circuit to see how the high and low pass circuits affect the frequencies. This is the high pass run. We are inputting a 20 to 20,000 Hz frequency sweep. The top left chart shows the input and output frequencies as they are inputted into the DAC. The bottom left graph shows the input frequency distribution and the bottom right graph shows the output frequency distribution. The top right graph shows both of these functions together. As you can see, the high frequencies are amplified in the high pass circuit. All of these graphs show an amplitude versus frequency.
We turned our circuit into a low-pass circuit by taking the op-amp output wire and connecting it to the capacitor, and taking the computer input wire and connecting it to the resistor. Here is our low-pass circuit built in LT Spice. We set the frequency to 589 Hz. Our output is now in red on the graph. As we can see, it has a phase shift of negative 90 degrees, and the gain is 0.9 for positive voltage and 1.05 for negative voltage.
After changing our frequency to 100 Hz, our phase difference remained the same, but we found that our output gain had some mysterious things. It had a gain of 4.5 for our positive voltages, but a gain of 7.5 for our negative voltages. We then changed the frequency to 1000 Hz. Our phase difference again remained the same, but we had a gain of 0.55 for our positive voltage and 0.63 for our negative voltage. We ran the LabVIEW VI with our low-pass circuit, as we did for the high-pass circuit, using the frequency sweep as our input. All the charts and graphs are formatted as before, and as you can see in the top right graph, the circuit amplifies low frequencies and blocks the high frequencies.